Okay, so we can go ahead and get started. We're a minute in. I just want to say hi, everyone, and welcome to today's knowledge session. My name is Kelly Giordano. I'm the Director of Digital Marketing and Media here at GIA, and we're very excited to have you as we explore diamond analysis for technological applications. Before we dive in, just a quick bit of housekeeping. Everyone is automatically muted during the session. If something comes to mind while you're listening, go ahead and drop your question in the Q&A feature at the bottom of your Zoom window. I'll be keeping an eye on those throughout, and I'll come back at the end to ask our speakers a few of your questions. We'll also send a recording of the session to you within the next day or so you can always watch it back on the replay. So now that we've covered the basics, let's meet our speakers. We're joined today by two of our experts in diamond defect analysis, Dr. Ulrika D'Haenens-Johansson and Dr. Daniel Jones. Dr. D'Haenens-Johansson is the Senior Manager of Diamond Research at GIA. Her area of research is the defect physics of natural, treated, and laboratory-grown diamond materials, with particular focus on developing methods for identification and separation. She manages the CVD lab at GIA, working towards creating reproducible growth procedures for the production of gem quality diamonds. She joined the GIA laboratory in New York as a research scientist back in 2011, following her master's and PhD degrees in physics at the University of Warwick in the UK. Combined, she has over 20 years of experience analyzing diamond defects. She's published research articles in scientific journals, including reviews in mineralogy and geochemistry, Physical Review B, Applied Optics, and our very own Gems and Gemology. And Dr. Jones is a research scientist at GIA, developing state-of-the-art instruments for researchers involving multidimensional imaging and spectroscopy of photoluminescence. He has a background in advanced spectroscopy and imaging of diamonds, in particular lab-grown CVD, with an emphasis on instrument development for lab-grown diamonds, which he's been working with for over 11 years. He joined the GIA research team back in 2022 following his master's degree in physics from Aberystwyth University, a master's degree in diamond science and technology from Warwick University, and a PhD in physics from Imperial College London. He's published several research articles in scientific journals, both on instrument development and analysis on CVD diamond. So with that, I'm going to pass it over to Ulrika and Daniel and get started.
Hi, good morning, afternoon, and evening. Thank you very much for taking the time to join us to discuss some of the capabilities that GIA has for diamond analysis for synthetic diamonds being developed for technological applications. Thank you for the introductions, Kelly. I'm Dr. D'Haenens-Johansson, and with me today I have Dr. Jones, and we are both part of the diamond instrument research teams at GIA. So I'd like to start by introducing our institute to you because our primary presence is within the gem field. So what is GIA? So we're the Gemological Institute of America. We're a nonprofit gemological laboratory that was founded back in the 1930s, and our main mission is to protect the diamond consumers and the gem consumers in the world through research, education, and unbiased gem grading and analysis. You might have heard about the 4 C's of diamond. That system, that standard, was created by the GIA. And in order to do this, we have laboratory services across the globe. We have 10 different laboratories where we primarily do grading and characterization of diamond, colored stones, and pearls. We also have a very active instrument development team where we customize and create our own in-house tools for gemstone analysis, whether it be for grading or spectroscopic tools for identification. And then finally, we are also an educational institution. You might have noticed that our website ends with .edu. So we also have several different courses that are available to the trade to gain an understanding on gem materials. So over the past couple of decades, there has been a significant improvement in diamond synthesis, and it has exploded within the gem field. From melee to multi-carat sizes, colorless to fancy colored, laboratory-grown diamonds are readily available now. Advances in the synthesis methods and its extended availability mean that diamond is now on the verge of widespread implementation for technological applications, and GIA is very excited to help support this next stage. In particular, as some synthetic diamond producers are starting to pivot away from growing gem materials towards growing diamonds for technological applications, they will find that they have notably different requirements, where properties of the material are tailored by careful defect engineering. It doesn't simply have to look good. With that in mind, GIA is excited to launch a pilot program where growers and application specialists can work with us towards meeting their goals, leveraging our deep understanding of diamond defects and our unrivaled combination of analytical techniques. And today we'll be reviewing the suite of techniques that we have available, the menu of techniques, if you will. So let's look at our background in a little bit more detail. Why do we think that we're in the position to help advance this field? Well, we're uniquely positioned for multi-technique analysis of diamond. So we have all of this in-house. We have well-equipped laboratories with advanced imaging, microscopy, and spectroscopic methods. We also have a vast experience analyzing, in particular, defects in diamond. We have studied millions and millions of diamonds as part of our laboratory services, providing us with this unrivaled data set of both the gemological and spectroscopic properties of natural, treated, and laboratory-grown materials. We also have in-house a CVD diamond growth laboratory where we grow our own CVD diamonds purely for internal research purposes, again, to gain an understanding of the fundamental properties of this material and do some defect engineering. We also have a big crew of experts. So we have a team of PhD level scientists such as Daniel and myself, postdoctoral fellows, research associates, and gemologists that conduct novel research on lab-grown and natural and treated diamonds in order to understand the defect formation and their evolution through treatments. And then finally, we disseminate all of this information through interactions with the trade at trade shows, at scientific conferences, and publications. So GIA research has been published in peer-reviewed scientific journals such as Science, Nature, Nature Geoscience, Optical, Optics Letters, Optics Express for some of our instrument development, all the way through our in-house Gems and Gemology journal. So let's look a little bit at sort of our background analyzing these materials. In particular, synthetic diamonds. So GIA has had its finger on the pulse when it comes to lab-grown diamonds from the get-go. So the first cuttable sized lab-grown diamonds produced by General Electric were analyzed at GIA back in 1971. You can see here that we issued a report that at the bottom says the conclusion that this particular diamond was a synthetic diamond with a weight of 0.305 carats. And on the far right, you can see sort of images of some of the diamonds that were analyzed at that stage. And since then, since 1971, we have been closely monitoring the development of laboratory-grown diamonds every step of the way. We publish comprehensive studies of HPHT grown diamonds from various sources, often as collaborative papers presenting a grower's novel products. And we have also published reviews tracking the development of gem quality synthetics submitted to our laboratory. So you can see this extensive suite of in-depth investigations into different HPHT grown materials. And we have also done so for CVD grown diamonds. So CVD synthetic diamonds, starting from the gem quality materials produced by Apollo Diamond in the early 2000s. Finally, we have also written extensive scientific reviews on the details of diamond synthesis and their identification, such as this example here on the right, showing a chapter of the Reviews in Mineralogy and Geochemistry, a RIMG volume, specifically on diamond. And in addition to that, we also publish reviews on the techniques that we use. So in our last winter edition of Gems and Gemology, it's a massive volume just going through all the different analytical techniques that GIA employs. But really, what is it that we're passionate about? One of our favorite things is to unravel the history of a diamond and understand its formation and evolution. And this applies to laboratory-grown diamonds as well. And the papers that we have here are freely available online on gia.edu, as well as the reviews on geochemistry the RIMG volume is also available freely online. So we'll be discussing some of these techniques today. So why diamond? Why are people so interested in diamond, both for the gem applications and the technological applications? For that, I will pass it over to Dr. Jones.
Thanks very much, Ulrika. So on this following slide, I will show you so that most people are familiar with diamond as a gem material, as we have discussed, but many of the properties which make diamond an amazing material for jewelry also make it an excellent material for industrial and technological applications. Diamond is mechanically hard, which makes it good for a variety of mechanical applications, such as abrasives, but it also has an unrivaled thermal conductivity, which makes it excellent as a heat spreader material. Pure diamond is also optically transparent, right the way from the UV to the IR wavelengths and beyond. It can become electrically active, which when coupled with its chemical properties, gives access to brand new applications. And now a novel new application of diamond are in the quantum field, where we look at, in particular, quantum sensing. But where does laboratorily grown diamonds come into this? So whilst natural diamonds can possess some or all of these properties, industrial technological applications require a firm, reproducible source. And this is where tailored lab-grown diamonds enter the field. So, for example, diamond can be used, as I said, as a heat spreader, as abrasives, as drilling components. This exploits its mechanical and thermal properties. But when looking at optical components, such as these optical windows here, we can see that the optical transparency of diamond from the UV to the IR becomes incredibly important, as well as coupling in with some of its more mechanical properties. Diamond can also be used as a pH sensor and also used for water treatment. And then finally, I discussed in this image here, we can see some of the quantum applications of diamond, where we're using the nitrogen vacancy defect in diamond to look at the magnetic field on atomic level scales. There are also, of course, military application, diamond domes, detectors in hostile environments such as nuclear reactors, and also masers. You may be familiar with lasers, which are visible wavelength devices. Diamond can operate as a maser, which is basically a microwave laser, and it's the only room temperature maser. So thank you very much. Ulrika, would you like to discuss what controls these properties?
Diamond is quite a simple structure, really. It's just a tetrahedral arrangement of covalently bonded carbon atoms. This structure, though, is precisely what leads to diamond's extreme hardness, thermal conductivity, and optical transparency. So here we have sort of a cartoon of all of the carbon atoms, just a projection. But perfection is not really always what we want. Often it's the imperfections and the defects that make it even more interesting and widen its range of applications. You could have missing atoms known as vacancies. You could have clusters of missing atoms. You could have substitutional defects, so where a carbon atom is instead replaced by something else, in this case, the boron atom. You could have nitrogen that's replacing the carbon atoms. And you can have complexes of more than one or two or three even different types of impurities that are placed next to each other. You can have complexes that involve substitutional material, substitutional elements, as well as vacancies, and much more complicated structures as well. And although the slide is really just showing nitrogen and boron related defects in diamond, you have other elemental impurities as well. In particular, now through lab-grown diamond synthesis, it's possible to intentionally dope using different elements. And each one of these has its own range of potential applications that is still currently being explored. Let's look at some of these in a little bit more detail. For instance, you could have boron that's present in the material. And in the gem world, we're excited about that because it makes a diamond pretty. It makes it blue. However, in the technological applications, by boron doping, you're able to manipulate the electrical conductivity of diamond. Diamond, if in its intrinsic form, is an insulator. However, by doping with boron, it's possible to go into the semiconductor, ultimately towards the conductor phase. And this means that the material can have applications such as electrochemical applications for wastewater treatment. Another defect that people are very interested in is the nitrogen vacancy center. In the gem world, we're excited by it because it makes a diamond pink, which is pretty, again. But it has applications, as Daniel touched on, in quantum sensing. So sensing magnetic fields, temperatures, strain, and electric fields. It can also potentially be used as a qubit, the building block for quantum information technologies. And then finally, there are some biomedical applications where it's being used as a luminescent marker. So what are GIA's analytical capabilities? Let's look into those into greater detail. So GIA has an extensive toolkit, as I sort of briefly mentioned previously. We have spectroscopic techniques that allow us to look at the presence, absence, relative concentrations, and potentially distributions of these defects, both point defects and extended defects within the diamond materials. And for that, we have absorption techniques such as UV-Vis-NIR absorption, FTIR absorption, Raman scattering, photoluminescence, fluorescence lifetime analysis, and then EPR spectroscopy. So we'll be going through all of these in today's presentation. And then we have imaging techniques. So imaging of the fluorescence distribution of defects, so fluorescence imaging, scanning electron microscopy and its accessories, cathodiluminescence, optical microscopy, and X-ray computed tomography. So when it comes to spectroscopic methods, oftentimes what we're looking at is the interaction of light with the diamond. So diamond is a wide bandgap semiconductor where the valence band and the conduction band is separated by about 5.49 electron volts. What does this mean? Well, for light to be absorbed by a perfect high purity crystal, the light has to have an energy greater than this value. This means that diamond is transparent from the infrared through the visible and into the ultraviolet. And this is what makes it such a great optical window. It's extreme transparency. Here we have the spectrum that can be collected. So the absorption as a function of the wavelength, which really demonstrates that other than some relatively weak absorption due to crystal vibrations in the infrared region, the diamond does not absorb much light at all. And to probe the absorption of a diamond, we rely on absorption spectroscopy that can then be divided into UV-Vis-NIR, or if we're probing the IR region, we use a technique called FTIR. Now let's introduce some defects. Defects introduce energy levels between the valence and the conduction band. This means that suddenly visible light can be absorbed. And something that's very useful to us is that the absorption is proportional to the concentration of the defect. So this is a quantitative analysis. Additionally, the absorbed light can potentially stimulate luminescence or fluorescence from the defect in question. So let's look at UV-Vis-NIR absorption spectroscopy. This is a technique that we use to determine the combination of defects, primarily that are responsible for the color in the diamond, providing information that can help us unravel its growth and treatment history. Now note that because we are working with very high sensitivity systems, oftentimes at liquid nitrogen temperatures, it means that we are able to collect spectra for these materials, even if by eye, we cannot detect any color. So we have very, very high sensitivity to these defects. At GIA, we're equipped with a suite of commercial instruments, as well as key GIA developed custom instrumentation that allow us to collect absorption spectra between 200 nanometers and 1,100 nanometers with variable resolution. It has flexible sample geometry. We work with anything from a small melee diamond to a large faceted stone to rough materials or plated materials as well. So we have a lot of flexibility built into our system. And here you can see that even though you have potentially two diamonds that look yellow, they have vastly different absorption features. So this allows us to identify what defects are present in the diamond. And then also one of the things that we're interested in is photochromism. So many defects in diamond can exist in more than one charge state, i.e. they have a different number of electrons. These defects are also oftentimes photochromic, where you can manipulate the charge state by applying light of certain wavelengths. At GIA, we're equipped to study this property by coupling a GIA-designed UV visible absorption system with a tunable light source. Here you can see how we can change the charge balance of the nitrogen vacancy center, in this case shifting the color of the diamond from orange to pink depending on the lighting conditions. And these type of defect charge state manipulation can have very important implications in the technological world as well. The other method that we use is looking at the absorption of infrared light. When diamond absorbs infrared light, the bonds between the atoms and the molecules will absorb some of this light, causing them to vibrate. And this is what we're measuring. And in the intrinsic diamond absorption, we can observe a little bit of absorption from the diamond bonds, so the carbon-carbon bonds, but we can also look at the presence of defects. So in particular, we're looking at the presence of and different forms of nitrogen and boron-related defects and impurities in diamond. And this is the foundation for what's known as the diamond type classification system. So essentially, if the diamond contains IR detectable nitrogen, it's considered to be a type 1 diamond. If it does not contain nitrogen in the IR, it's considered to be a type 2 diamond. And you get further branching, as you can see here. In the technological world, generally people are working with a type 2 diamond. So whether they are pure with no nitrogen, the type 2A diamonds, or potentially the ones that have boron in them, the type 2B diamonds. And when we do this collection of FTIR absorption spectra, one of the key things is that we're able to quantify the concentrations of these defects, such as the boron or the isolated nitrogen or other complexes. Additionally, we're able to do FTIR mapping to probe the defect distributions. So on the top, we have an image of a HPHT grown type 2B diamond, a plate that has been cut from that. And we can see that certain growth sectors within the material in the white light look very blue. And this is due to the presence of boron. So you can see on the right that there is a FTIR map that has been created for the HPHT diamond, and we can see the boron concentration varying across the different growth sectors. And then in the bottom, we have an example from a natural diamond that has different forms of nitrogen, and we're able to deconvolve them and look at the concentration of the isolated nitrogen versus other nitrogen-related defects in the IR. And again, we're equipped to analyze a range of different geometries and sizes, rough, faceted, and plated diamonds. So with that, I'm going to transfer onwards to Daniel, who will be discussing a different form of spectroscopy.
Thank you very much, Ulrika. So whilst so far we've discussed looking at broad spectral bands, looking at sometimes in the case of IR, very, very, very broad spectral excitation or illumination. In this case, we're going to discuss probing with a very narrow spectral width laser, for example. And typically, under most circumstances, said laser would just reflect off the surface of the diamond, for example. But under very rare circumstances, some of the energy of that laser is actually lost to those lattice vibrations within the diamond itself. And when the laser comes back, it has a slightly reduced energy. And we call that a Stokes shift. And this is the basis of Raman scattering. And Raman scattering is very important for diamond analysis. So on the following slide, I will show you that the diamond Raman peak is at 1332 wave numbers, which is basically the units for Raman's Raman spectroscopy. And we can see there in that spectrum a very, very nice line, very, very narrow at 1332 wave numbers. Now, why is this important? First of all, it's a spectral fingerprint of diamond. You can use this to basically characterize, you know that this is a diamond that you are looking at. But the Raman peak in particular can also be used to evaluate strain in the material. So it will broaden as the strain in the material increases. It may also shift position or split. And as it gets narrower, there is less strain in the material. So this is a mechanism that you can use to study the bulk or indeed the individual strain characteristics of a diamond. And it can also be used to non-destructively analyze mineral inclusions. So this is an example of a series of mineral inclusions inside a natural diamond, and you can see that each one of those materials, each one of those mineral inclusions has a unique Raman signature. So it's very critical to say what equipment we use for this. So we have a series of commercial instruments, but also some GIA specific instruments. So we can do point analysis or mapping on this. But somewhat related to Raman scattering, on this next slide, I will show you a different process, which Ulrika has sort of hinted at so far, called luminescence or fluorescence. This is where some of that light that is absorbed by the diamond actually comes back and is re-emitted with a slightly different color or wavelength, different to the light that went in. We call this photoluminescence spectroscopy, which I will show on the next slide. So this is a photoluminescence spectroscopy or PL spectroscopy, and this is a very, very, very powerful technique. First of all, it uses the same equipment for the Raman analysis, you use a series of excitation wavelengths, lasers. In the GIA, we have access to the deep UV at 325 nanometers, right the way through to 830 nanometers in the near infrared. So a whole slew of wavelengths. But why are those wavelengths important? What do they tell us? So in the bottom right-hand corner, you can see a series of spectra, 4 spectra, all collected from the same sample at 4 different excitation wavelengths, going from 325 to 633 nanometers. And what you can see is that different spectral features are present, and those spectral features are the fingerprints of different defects. For example, the nitrogen vacancy defect that we have heard all about, H3 and H4, these are different type of defects within diamonds that may have different applications. And the ability to use different lasers to excite those allows us to be very sensitive to their detection. So Whereas the absorption techniques that you have heard about so far typically require relatively high concentrations, many parts per million in some cases, of defects present, it is possible with PL spectroscopy to be sensitive to individual atomic defects within the diamond, individual nitrogen vacancy centers, for example. So we're talking parts per trillion, parts per billion levels of sensitivity, and that makes it a very, very useful tool for looking at diamond that may be suitable, for example, quantum applications. But unlike absorption spectroscopy, it's only semi-quantitative. Absorption spectroscopy can, under some cases, be fully quantitative. However, PL spectroscopy is only semi-quantitative. You can do work such as look at the Raman line normalization, which might get you a comparison between regions on the same sample. But fundamentally, absorption is better suited for that under some circumstances. We are equipped for data collection from the liquid nitrogen ranges all the way up to 600 degrees Celsius. And again, we have a series of commercial and GIA developed instruments that we will discuss a little bit later. And this is capable of looking at bulk analysis, individual points as per confocal analysis. This is where you're looking at very, very small volumes of emission from your sample. And we can also do mapping, and that's some examples of which are shown there, where we are mapping the nitrogen vacancy at 2 different charge states, as you can see in those maps, and correlating that with a different type of imaging technique. On the next slide, however, I would like to discuss a unique instrument that we have developed at GIA. So whilst most institutions that may have access to PL mapping typically are only looking at this in 2-dimensional slices, diamond is and most things are 3-dimensional objects. They have a X, Y, and Z extent. And so at GIA, we have developed a unique 3-dimensional hyperspectral photoluminescence imaging system. And this, again, allows us to look at the photoluminescence defect distribution within a sample without destroying the sample. And this allows us to get significant amount of insights that we wouldn't typically have. We have a series of excitation wavelengths. And on this next image that I will show you, this is just an example of what the data looks like. So in this case, I'm just showing you a 2-dimensional representation, although you may note that there are 3 dimensions there. So in this case, we have an X coordinate and a Y coordinate, and then you can see that there are different colors moving into the plane, different wavelengths. So we call each one of those cubes a voxel, a 3-dimensional pixel, you can think of that. And each one of those pixels contains a spectrum, and that can be independently analyzed and allow us to identify the defects which are emitting. So you can see here the case of emitter A and emitter B located at 2 different regions on that XY image, and looking at the depth information, which is in this case spectra, to extract the sort of the fingerprints of the species. We can of course repeat this many, many times and build up X, Y by lambda and the Z number of images, which is a 4-dimensional data set. I wouldn't recommend trying to think too hard about that one because it's quite complicated. I struggle myself, but we can manipulate this data to reveal how natural or laboratory grown diamonds are made, and looking at changes in the point and extended defects from the rim to the core. So I wanted to show you an example of this. So on the left-hand side, we can see a GIA-grown CVD diamond, a substrate at the bottom with the CVD diamond grown on top, intentionally varied to produce different colors in this case. But what does this look like under the 3-dimensional hyperspectral imaging system? So on the following image here, this is an example of the 3-dimensional image. So I've distilled that 4-dimensional data set down to a 3-dimensional data set of 3 different colors, in which case the colors correspond to the green color is the GIA grown CVD diamond, which was grown on top of the substrate or the seed, which is the blue color that you can see in this data set. And then you can see the orange layers or red layers, which correspond to the growth interruptions. And basically what you're seeing in that image there are different cross sections. And this can be used to identify changes in the growth morphology and defect incorporation, obviously something important for CVD growth process, because you can then correlate that with the growth conditions. So in the next image, I just want to show you what the actual surface looks like. So if we look at that purple line across across the center of the image there. What you were looking at in the bottom, which is the XZ image, that is the growth surface of the CVD diamond as it was in the reactor. This is basically a time machine that you can use to go back in time and see what your growth layer looked like in the reactor as it was growing. And as I said, this technique is non-destructive. And as far as we're aware, it's the only technique that can reveal these details. And on the next slide, I'd like to show you a video of basically what the growth surface of this diamond looked like as it was growing in the reactor. So if you look at the mouse arrow on the top image, you can see I'm moving up through that diamond from the bottom, and that bottom image is that growth surface. This is what the diamond looked like as it was in the reactor, and the different colors correspond to basically different defects being incorporated into the diamond as it was growing. But on the next slide, I'd like to simplify things ever so slightly and just go back to a 2D analysis. So of course, we don't have to use this instrument to look at a full 3-dimensional volume. We can look at this in 2 dimensions as well. So this is an example of a uninterrupted 6-layer sample that was grown at GIA. And you can see from the white light transmission image there that we have the substrate at the bottom, which is brown, and then the diamond that was grown above it is clear. But when we use deep UV fluorescence imaging, we can clearly see those layers, and we can see that they're different colors and also different strengths, they're different intensities, so to speak. And we can use this system to have a look at, in this case, 3 specific defects, the 468, 575, and 367, which are the nitrogen vacancies in their 2 charge states respectively. And we can look at the fine detail of these and get an idea of how the defect incorporation varied on the micron scale within this diamond. And we can also plot line profiles, as you can see here. So these are line profiles going through from the substrate up to the growth surface, and look at, with very fine detail, how the different defects are being incorporated during growth. But I really want to illustrate that while you've seen monochromatic and these false color images that I've shown you, fundamentally the data that was underneath that are these spectra here. So these spectra were collected from that 4-dimensional data set that we acquire for this, or indeed for any type of the analysis. So we can extract this spectral information, which allows us to perform the fingerprinting that is required to construct those images. This is a very, very powerful technique. But on this next slide, I'd like to talk to something a little bit different. So we've discussed fluorescence so far, but it's not the emission wavelength isn't the only property of fluorescence that we care about. There's something called the fluorescence lifetime, because it turns out when an electron gets excited, gets absorbed, gets absorbing some of the energy of the light that is shone on the sample, it doesn't immediately decay down from the excited state. It will, on the next image, it will show, it will stay in there for a certain amount of time. The electron will linger in this excited state for a random amount of time, and then it will decay. So it will emit light as fluorescence, as we have seen, as it decays from the down to the ground state. And basically, the average amount of time that an electron will stay in this excited state for, we define as the lifetime of that specific defect. And basically, this value is different for each defect in diamond. For example, the nitrogen vacancy has a lifetime of approximately 19 nanoseconds. We're talking billionths of a second. This is a very, very fast process. But why is this important? So not only can we use the lifetime to identify what different defect we're looking at based on its lifetime, it also gets reduced by nearby defects, some of which you may not be able to see that are only visible in absorption techniques. And so lifetime measurements are significantly more sensitive under some circumstances for looking at low concentrations of nearby defects. And in this next slide, I'd like to show you an example of that. And of course, because we couldn't possibly get away from the 3-dimensional imaging side of things, so we've actually developed an instrument that is capable of measuring the distribution of this lifetime in 3 dimensions, so X, Y, and Z. So in this case here, we're looking at the N3 defect. We have the intensity shown at the top, and then on the bottom, we have the N3 lifetime. And you can see that there is significantly more contrast present in this image. And this is a 3-dimensional data set that we are looking through. So you're looking at the 3-dimensional volume of this diamond. And the contrast mechanism here is the lifetime, but what that's controlled by is the concentration of a defect called the A center in diamond, which is a pair of nitrogen atoms. And we are able to calculate the concentration of that in 3D using this technique. And now I will hand it off to Ulrika to discuss EPR. Thank you.
Thank you, Daniel. So the final spectroscopic technique that we'll be looking at today is electron paramagnetic resonance, EPR. You might have also heard of it as electron spin resonance. So this is a technique that is sensitive to defects in diamond that have unpaired electrons, such as the isolated nitrogen, the nitrogen vacancy center in the negative charge state, as well as a few others. Now, this is a bulk technique, but EPR can measure defect concentrations down to less than 1 part per billion, depending on sample volume and defect species in question. And the reason that this is important, in particular for technological applications, is that electronic grade synthetic diamond is typically defined as a diamond that contains concentrations of isolated nitrogen less than 5 parts per billion. And this technique, EPR, is the only quantitative technique that can measure down to these type of sensitivities. SIMS or FTIR have nowhere near the same type of detection limit. So we're not able to use SIMS to, for instance, characterize a diamond that is this high purity. EPR is the only way. And at GIA, we routinely use EPR for the analysis of isolated nitrogen defects in diamond. And we have a huge experience doing this for both CVD and HPHT and natural diamonds. So moving on to some of our imaging capabilities, the second prong. So one of the techniques that is particularly useful is fluorescence and phosphorescence imaging. So we're able to induce fluorescence in diamonds using a range of different illumination, long wave, short wave, and deep UV illumination. But the key one here is using deep UV, i.e. very high energy UV light, wavelengths less than 225 nanometers. And this will induce a fluorescence response in virtually all diamonds, with the fluorescence emission coming from very close to the surface of the material, giving you very nice, sharp, clearly resolved images. And this is something that we use to reveal the diamond's intrinsic growth and deformation patterns. So you can see at the bottom, we have some natural diamonds, we have some lab-grown diamonds as well, and they have vastly different patterns. Now, the colors that we're observing relate to the emission wavelengths of the luminescing defects, and it can help indicate changes in growth conditions and treatments. And then depending on the material in question, we might be able to look at it and be like, oh, it's emitting red. In this case, a CVD diamond. The defect that's associated with that is the nitrogen vacancy center. So it can give us really good information, easy to acquire information on the distribution of these defects. And here we have an example of sort of what we'd be looking at for, say, a CVD synthetic diamonds. When CVD synthetic diamonds are growing, the deposition is typically through step flow growth. So you have a series of terraces and risers going at the surface of the material. Once you cut and polish it, you wouldn't be able to see these features. However, the incorporation of defects will vary on this material. So for instance, the defect that is here illustrated in orange loves going into the risers, but hates going into the terraces. As you grow your material thick enough, you're going to end up with a series of striations. It's producing this sort of contrast in the color of these, contrast in the intensity of the luminescence. And most CVD diamonds will show striations. Additionally, we might be able to observe dislocation bundles that are associated with blue band A emission, especially in high purity materials. Additionally, any type of changes in the growth conditions, whether it's intentional sort of interruptions or changes in, say, the gas chemistry, the temperature, anything like that is going to lead to layers and interruptions that we can observe as well. So here we have an example of some faceted CVD gemstones that have come through our laboratories. On the top, we have some as-grown materials. They're emitting red and pink hues due to the presence of the nitrogen vacancy center. We can see that there are striation patterns, these finely spaced lines across all 4 of these diamonds. And then on the top left, we can see that the as-grown diamond in particular, on the top left, has these very clear interfaces going through it. And that's because they grew this diamond through multi-layered growth. So they grew, stopped, prepared it again, and continued growing over and over and over. And then on the bottom for the treated examples, we can see that those are emitting in green instead. The patterns are the same, but the emission color is different because they have treated these stones to decolorize them, producing instead, for instance, defects such as the H3 center or other features that fluoresce in the green and blue. Now for CVD diamonds, if you have a block, it's very important to analyze different features, different sides of the material. So here we have a CVD diamond block. On the top growth surface, we can see this red emission due to a nitrogen vacancy center, and closer to the edges, closer to where originally there would have been a polycrystalline rim, we can see that the growth is sort of starting to fall apart. There's more dislocations illuminated in blue. And then if we look at the cross section, we can see that this particular sample is grown over 3 layers on the seed. And we can see that as the growth was progressing, we see the same, reasonably the same concentration in the MV centers, and the color looks the same, the red emission with the striations. But we can also see that at each layer interface, you might be introducing more dislocations shown in blue. So this allows us to understand how our diamond is growing and at what stages we're introducing certain defects. Similarly, for HPHT diamonds, the defects, the impurity uptake differs for different growth sectors. HPHT diamonds proceed through a cuboctahedral growth morphology instead of the step flow growth. But we're able to identify which growth sectors are present in the material by using this deep UV imaging, in particular, even in colorless material. Other imaging techniques that we have in-house include a scanning electron microscope that is equipped to do a range of different imaging techniques using different accessories. So using secondary electrons, we can image the topography of materials. Using backscattered electrons, we're able to detect differences in the chemical composition, for instance, detect coatings as shown in the top right, or expose inclusions. We can use EDS to analyze the emitted X-rays and provide us information about the chemical identity and the elemental identity of the materials that are present in the diamond, as well as photoluminescence. So in the same way that Daniel was speaking about luminescence techniques where light was inducing the luminescence and the emission of light of the defects in the diamond, you can also excite those defects using the electrons from the scanning electron microscope. So we collect the photoluminescence imaging. And the great thing with this is we're able to do this in much, much higher magnification, high resolution. And here we have some examples of some photoluminescence images that we have collected on CVD synthetic diamonds. So a faceted stone on the top left that has these clear interfaces, these clear layers as it was grown over with a stop-start growth procedure. We can see on the bottom striations, very fine striations. And then in the middle, we can see this image that was collected on a high purity CVD diamond with these sort of polka dots going through it. And those are the individual dislocations that are threading up through this surface. So we can use this, for instance, to estimate the density of the dislocations present in the material. And then for HPHT grown diamonds, we can again see the growth sectoring that is present in the material using photoluminescence. And then we have more sort of standard optical microscopic techniques. We have several research grade microscopes that are available for microscopic observations and documentation with dark field, bright field, fiber optic illumination, and additionally differential interference contrast microscopy as shown on the bottom right. So that gives us a very good idea of the topography of the material. And then here we have some examples of the same sample being viewed under different lighting conditions. So transmitted light gives you information on the color. It gives you information on whether there are any inclusions in your CVD grown diamond. The reflected light gives us information about the topography. And then between cross-polarized filters, we're able to visualize the birefringence pattern and get an understanding of the strain that's present in the diamond. And then on the bottom, we have some examples of some images that we have taken of CVD diamond etch pits. So CVD diamond has been placed into the CVD reactor and etched using a hydrogen oxygen plasma to reveal the location of threading dislocations. And again, this is a tool to understand the dislocation density within the material. And then finally, we have X-ray computed tomography. This allows us to create a 3D model of an object from a series of X-ray projections collected as it rotates. So here we have an example of a natural striated diamond that contains inclusion clouds. So you can see those now showing up on the right as it sort of changes the transparency. And from this, we're able to create 2D cross sections and analyze things in great detail. So we can use this for imaging inclusions in diamond. We can use this for imaging diamonds in xenoliths, so the rocks that bring the diamonds up. Essentially, this is unexplored. This technique is yet unexplored for imaging components that integrate diamonds. So there are applications for this for understanding, say, devices that contain diamond materials as well. Okay, but we have several applications, but do we know anything about diamond growth? We do. So in addition to analyzing materials that are grown by others, GIA does have an in-house chemical vapor deposition laboratory. So equipped with two different instrument designs. And we also have experience looking at the material as it's growing and analyzing the plasma using optical emission spectroscopy. So here we have an example of a video that's showing one of the GIA CVD grown diamonds as it's progressing through growth. And really the key thing here is this just demonstrates that we have experience doing defect engineering and recipe development. We understand the type of data that is necessary to improve growth processes. And then along with that, we obviously have sample preparation and treatment facilities. So we are able to do laser cutting of diamonds. We have polishing wheel to polish, say, CVD grown cross sections, for instance. We have acid cleaning capabilities. And then we also do in-house diamond treatment using a range of different tube furnaces and LPHT systems. And this can be under vacuum or under other environments. And really here, what we really want to conclude with is that GIA is launching a pilot program to analyze laboratory-grown diamonds for technological applications. We have a vast menu of techniques available, including commercial and GIA-developed tools that have specifically been developed for looking at diamond. And by combining our vast suite of spectroscopic and imaging techniques, we're able to gain a multifaceted overview of the key properties of diamond materials. Now, this data can be used to verify that requirements on defect concentrations or distributions have been met, for instance, isolated nitrogen concentrations. And this data can also be used to support the feedback loop necessary for synthesis recipe development, i.e., companies that are now trying to pivot from gem quality growth, where the material might have originally been brown and turned colorless through treatment. Now they're able to use this type of information to work towards developing recipes for super high purity growth. So for any inquiries that anyone in this audience has on this new pilot program or our techniques, please do not hesitate to contact Dr. Wui Wang at diamond@gia.edu. And we are open for questions. Thank you very much.
I have to say, I know I'm just a humble marketer, but it never ceases to amaze me the brilliance and all the work that my colleagues do in the research team. This is such a fantastic presentation. We don't really have any questions in the Q&A panel, so I'm assuming that you just covered everything, Ulrika and Daniel. So, but I know this is a lot to process. There's a lot of great information here. So if any of you have any questions after we wrap, as Ulrika said, please do reach out and email us at diamond@gia.edu. And one of our research members will answer your question. If you were able to join us live, I just want to say thank you so much for joining us. You've been a wonderful audience. And if you're watching the replay on YouTube, don't forget to like, subscribe, and leave a comment with any questions you have. And again, you can also reach out to us anytime with questions at diamond@gia.edu. So thanks again for spending part of your day with us. And we hope to see you at another GIA Knowledge session soon. Thank you, everyone.
Thank you.
Thank you.